Uranium does not become nuclear power because a rock glows in the dark. It becomes nuclear power because that rock enters one of the most controlled industrial chains on Earth. The hidden process starts in a mine, then moves through chemistry, gas, spinning machines, ceramic pellets, metal tubes, and security. Only after all of that can a small piece of uranium sit inside a reactor and help power a city. The first answer is simple. Nuclear power is not made by burning uranium like coal. It is made by turning uranium into a carefully engineered fuel, then using atoms inside that fuel to release heat. That heat boils water, steam spins a turbine, and the turbine makes electricity. The hard part is everything before and after that moment. Fresh uranium from the ground is not ready for a reactor. Most natural uranium is uranium-238. Only about 0.7% is uranium-235, the type that splits easily enough to support a chain reaction in many power reactors. So the real story is not just finding uranium. The story is separating it, cleaning it, shaping it, guarding it, and later storing what it becomes. That is why uranium feels different from coal, oil, or gas. You do not simply dig it up and throw it into a fire. You turn a heavy mineral into a precision energy cartridge. Every step adds power. Every step also adds cost, risk, and responsibility. Start at the mine. Uranium can come from open pits, underground mines, or in situ recovery, where liquid dissolves uranium underground and brings it back up. At this stage, the ore is not a glowing superhero stone. It is usually ordinary rock with a little uranium mixed inside. The danger is not only radiation. Mining also means dust, heavy metals, chemicals, water risks, and waste rock. Nuclear power can produce huge energy from tiny fuel volumes. But the fuel begins with mining, and mining always leaves a footprint. Then comes milling. The ore is crushed and treated so uranium can be separated from the rest of the rock. The result is a dense uranium concentrate, often called yellowcake. The name sounds almost friendly. It is not cake. It is a regulated industrial powder, usually made mostly of uranium oxide. And it is still not reactor fuel. Think of it like flour before bread. Useful, valuable, and still far from finished. To move closer to fuel, yellowcake has to enter another chemical step. Uranium oxide is converted into uranium hexafluoride, which can become gas when heated. That gas matters because the next stage is enrichment. Enrichment is the step people often hear about in news stories about weapons, treaties, and inspections. For many commercial power reactors, enrichment raises uranium-235 from about 0.7% to a few percent. That sounds tiny. It changes everything. It gives the reactor enough easy-splitting atoms to keep a controlled reaction running. Modern enrichment is usually done with centrifuges. Imagine thousands of tall, narrow machines spinning at extreme speed. Inside them, uranium hexafluoride gas spins until tiny weight differences start to matter. Uranium-238 and uranium-235 behave almost the same chemically. But uranium-238 is slightly heavier. A single spin does not do much. The process repeats through many machines until the mixture slowly changes. One stream becomes enriched uranium. The other becomes depleted uranium, which still contains uranium, but less uranium-235. This is why enrichment is sensitive technology. For power plants, the enriched uranium has to be changed again. The gas is converted into uranium dioxide powder. That powder is pressed into small ceramic pellets and baked until the pellets become hard and dense. A fuel pellet can be roughly the size of the tip of your finger, yet it can hold an astonishing amount of usable energy. That is the everyday shock of uranium. Rock becomes tiny ceramic pieces stacked inside long metal tubes. Those tubes are fuel rods. Fuel rods are grouped into fuel assemblies. Fuel assemblies are built for one reactor type, with exact dimensions, materials, and limits. At this point, fuel is no longer just fuel. It is a machine part. If a dimension is wrong or heat is not removed properly, the issue can become serious. The hidden design choice is control. Every pellet must release heat predictably. Every rod must contain radioactive material under harsh conditions. Every assembly must let coolant flow through it. Inside the reactor, uranium is not exploding. It is doing something slower, controlled, and useful. Uranium-235 atoms split when hit by neutrons. That split releases heat and more neutrons. The reactor manages the chain reaction, so heat comes out steadily, not violently. That steady heat is why a small amount of fuel can produce so much electricity. The front end of the uranium story is about making fuel. The back end is about living with what the fuel becomes. After years in a reactor, fuel assemblies are removed because the material inside has changed. Some uranium has been used. New radioactive elements have formed. The fuel is still extremely hot and highly radioactive. It cannot be tossed aside or forgotten behind a fence. First, spent fuel usually goes into deep pools of water. The water cools the fuel and helps shield radiation. Later, many assemblies can move into dry casks made of steel and concrete. This is where the promise of nuclear power meets the part nobody loves to advertise. The waste volume is small compared with the waste from burning fossil fuels. But small does not mean simple. Spent fuel needs isolation, security, monitoring, and decisions that can outlive the people who used the electricity. Some countries reprocess spent fuel to recover usable materials. Others store it and plan for deep geological disposal. Reprocessing can recover energy value, but it adds cost, chemistry, security concerns, and debate. Direct disposal avoids some extra processing, but it requires a repository society will build and trust. That is why uranium is both powerful and uncomfortable. The front end feels like engineering. The back end feels like a promise made to the future. The entire system only works if every link holds. Mining has to be managed. Milling waste has to be contained. Conversion and enrichment have to be secured. Fuel fabrication has to be exact. Reactors have to be operated with discipline. Spent fuel has to be stored for decades, then handled with an even longer plan. The dangerous process behind nuclear power is not one dramatic moment. It is the chain. Each step makes the next step possible. Each step also creates a new responsibility. Supporters point to huge energy density and low-carbon electricity. Critics point to mining damage, accidents, waste, cost, security, and weapons risk. Both sides are looking at real parts of the same machine. Uranium can produce massive electricity from a small amount of fuel. It also demands control from the first drill hole to the final storage site. So when someone says nuclear power comes from a rock, they are only telling the first inch of a very long story. The real power comes from chemistry, physics, machines, regulation, patience, and trust. The power is real. The chain is the danger.